right, so we want to start talking about arc length. And we're going to utilize the same idea and strategy that we did earlier on, which is we are going to use the power of infinitesimals and calculus and limits to figure out the arc length of something that is not straight, right? Because if it was a straight line, we could figure out the length pretty easily. But when we have something that's not straight, we're going to have to work a little bit more. So let's start by drawing a picture to give us an idea of how this would work. So let's imagine we're trying to find the arc length of this curve between the numbers a and b. And we're going to do the same thing that we've been doing. We'll subdivide it into a bunch of different subregions, and then imagine we could connect each of those pieces with a straight line segment, right? So we could do something like this. So all of those straight line segments wouldn't be exactly the same length, right? But it wouldn't be a terrible approximation. But here's the idea of how we can find that. So now imagine on each of those little teeny line segments, we could make a little teeny right triangle, right? So let's zoom in on that little piece right there and see what we get. So if we were to zoom in, on that piece, we get something that looks like this, right? Well, the distance in the horizontal or the x direction would be our delta x. And the distance that we went up would be our change in y, right? Our delta y. Both of those are measurable, right? Because we have the function. We know how much it was at this point, and we know what it was at this other point, right? We also know the distance between these two things. So these are known quantities. But we've now made a little teeny tiny right triangle. So if we know the two legs of a right triangle, how do we find the length of the hypotenuse? Pythagorean theorem, right? So a squared plus b squared equals c squared. So that tells us then, if a is delta x and b is delta y, then c squared is delta x squared plus delta y squared. But then c would be the square root of all of that, right? That's just our Pythagorean theorem. So we get what I'm going to refer to as the arc length. And so it's customary to let S represent the arc length. So let S be the arc length. Then delta S is equal to delta x squared plus delta y squared, right? So then we could look at this and let's factor this in a very creative way. So we are going to factor out a delta x. So to do so, if we factor out a delta x squared underneath the radical, so delta x squared, out of our first term we have a delta x squared, and if we factor out a delta x squared, that leaves behind a 1, plus the delta y squared doesn't have any delta x's, so that would be delta y over delta x quantity squared. And we can check by distributing that back in that if we did, the delta x's in the denominator of the second term would cancel out, and we would end up with delta x squared plus delta y squared, right? So it's the same thing. And then finally, we have a product, so the square root of delta x squared is going to be delta x. So finally, we get 1 plus delta y over delta x squared times delta x. So this is our approximation for each of those little teeny arcs, right? Yes, sir?
Delta x is outside the radical, right?
Yeah, it is in the second one, yes. So delta s represents the actual arc length, or each of the red bits in our little triangle, right? And if we added all of those up, we would end up with the arc length, right? But now, if we let the number of subdivisions in that AB interval go to infinity, so if we take the limit, what we're going to end up with is this. And what is delta y over delta x? The change in y over the change in x. That's the derivative, right? That's slope, right? The change in y over the change in x. So the change in y over the change in x is our slope. So this is y prime, right? So putting all of this together, we get that the arc length is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. And we can write that in either Leibniz or standard function notation. And if you look on your note sheet, there is a nice typed version instead of my handwritten version for each of these. And it says arc length formula. If f prime is continuous on the closed interval AB, then, not them, apparently that's a typo, then the length of the curve y equals f of x from a to b is given by the integral from a to b of the square root of 1 plus f prime of x squared dx, or in Leibniz notation we get the same thing. So basically, the idea is we just made it into a whole bunch of little teeny right triangles and then let the lengths of the sides of the triangles go to 0 to get the exact arc length. So that's pretty cool. So let's see if we can do our first example. So it says, find the arc length of f of x equals the square root of 1 minus x squared in the first quadrant. So let's draw a picture. So the first quadrant is where both x and y are positive. And if we were to graph this, what's that graph going to look like? So f of x and y are the same thing. So this is y equals the square root of 1 minus x squared. If we were to square both sides, we get y squared equals 1 minus x squared. Adding x squared to both sides, we would get x squared plus y squared is equal to 1. And what is that the equation of? It's the equation of a circle with center 0, 0, and radius 1, right? But we only want the part of the circle that's in the first quadrant. So if we graph that, it's just going to be this quarter circle hanging out in the first quadrant, right? Okay, well, since it's a quarter of a circle, do we know what the arc length is? Sure. What's the formula for the circumference of a circle? So the circumference of a circle is pi times d, or 2 pi r, right? But this isn't a whole circle. This is only a quarter of a circle, so we would have to divide that by 4, right? So then the radius of our circle is 1, so that would be 2 pi times 1 divided by 4 gives us pi over 2. So we know what the answer should be. We should get that the arc length is pi over 2. Let's see if that's true. So we have our function f of x is the square root of 1 minus x squared. So f prime of x is going to be, so this is 1 minus x squared to the 1/2. So our derivative is 1/2 times 1 minus x squared, take away 1 to the negative 1/2. Then by the chain rule, we multiply by the derivative of the inside. And the derivative of 1 minus x squared is negative 2x. So then f prime of x is our 2's reduced out. We get negative x over our negative 1/2 moves that factor from the numerator to the denominator, puts it back in a square root because it's a 1/2 power. We get f prime of x is negative x over the square root of 1 minus x squared. So that's our f prime, and our formula for the arc length is L is equal to the integral, and we're going to go from 0 to 1 of the square root of 1 plus f prime of x squared. So we have the square root of 1 plus f prime of x squared dx. And now we need to simplify. So 1 plus negative x times negative x is positive x squared. And if you square a square root, it reduces out. So now we need to get a common denominator. And our common denominator is 1 minus x squared. So that gives us the integral from 0 to 1 of 1 minus x squared over 1 minus x squared plus x squared over 1 minus x squared. And we're like, aha, something awesome happens. Negative x squared and positive x squared. So they reduce out. And that leaves us with the integral from 0 to 1 of the square root of 1 over 1 minus x squared dx. So then we can simplify that down just a teeny bit more, because the square root of 1 is 1. And then we have 1 minus x squared dx. So now we need to evaluate this integral. So which method of integration does this look vulnerable to? Okay, I hear u substitution. What would we choose for u? Okay, if we did that, then our du is negative 2x. Do we have an x to substitute out? No, we don't. So the u substitution's not going to get us where we need to be. When we had radicals, what was our strategy? Especially with things like 1 minus x squared. Trig substitution. So which trig substitution paired with a squared minus x squared? So let's see. That is x is equal to sine theta. Then dx is equal to cosine theta d theta. We have to change our limits of integration, so 1 equals to sine theta. If that's the case, if 1 equals sine theta, we take the inverse sine of both sides, so theta is the inverse sine of 1, and the inverse sine of 1 is pi over 2. We also have to solve 0 equals the sine of theta, and that gives theta equals the inverse sine of 0, and the inverse sine of 0 is 0. So our new integral looks like, well, when we put in 0, we get out 0. When we put in 1, we got out pi over 2. 1 over the square root of 1 minus sine squared theta times our dx, which is cosine theta d theta. And using our trig identities, what is 1 minus sine squared theta the same as? Yeah, so this is the integral from 0 to pi over 2 cosine theta over the square root of cosine squared theta d theta. But the square root of cosine squared is cosine, so those are going to reduce out, and finally we're just left with the integral from 0 to pi over 2 of d theta. So the integral of d theta is just theta, evaluated from 0 to pi over 2. Well, that's pi over 2 minus 0, which is pi over 2. Same answer we got using geometry, right? So it turns out for circles, we already knew how to do this, but the formula that we have from calculus is more general. We can use it to find the arc length of any differentiable curve. All right. All right, so let's go ahead and do this. So our function f of x is 4x. So f prime of x is going to be 4. So the formula for our integral is going to be from 1 to 4 of the square root of 1 plus f prime squared, so 4 squared, dx. So then that's the integral from 1 to 4. 4 squared is 16. 16 plus 1 is 17, so we have the square root of 17 dx. So square root of 17 is a constant, so it just comes out of the integral. And then we integrate dx, which is going to be x, and evaluate from 1 to 4. So we get the square root of 17 times 4 minus 1, which is 3. We get the answer is 3 square roots of 17. So if we draw a picture of this situation, we'll see why this integral turned out to be a lot easier than the other one. So here's 1, 2, 3, 4. And then over here we're going to scale in 5s. 10, 15. So if I put in 1, f of 1 is going to be 4. And f of 3, or f of 4 rather, is going to be 16. So f of 4 is going to be all the way up here at 16. So I'm looking for this distance of this line. But since it's a straight line, I can actually just count these things off, right? So my change in x is going to be 3, and from 4 to 16, my change in y is going to be 12. So by the Pythagorean theorem, 12 squared plus 3 squared gives us c squared. So c squared is 144 plus 9. And we need to solve for c. So we take our square root. So we need to simplify the square root of 153. Well, something that is helpful is 9 goes into 144 16 times, so we can factor a 9 out of both. And that's 16 times 1, or 16 plus 1. So then the square root of 9 is 3, and 16 plus 1 is 17. Or you could just simplify it, right? Because 9 goes into 153 17 times. So if you factor it that way, you get 9 times 17, and you get the same thing. Which is the same answer we got doing the integral, right? Just the Pythagorean theorem. It worked this time because 4x is a straight line, right? So we could use the Pythagorean theorem. There was no bending to said curve. All right. Let's take a look at our next example. So example number 2, I feel, is a very representative integral of the type we're going to run into when we're calculating arc length. So since the arc length formula has a radical in it, oftentimes we're going to need to do trigonometric substitutions. That was our strategy to reduce radicals out. So more often than not in this type, very innocent looking things like this turn into very, very ugly integrals. Because if you look at this function, it's just x squared over 2, right? And in fact, its derivative is even better. What's the derivative of x squared over 2? Well, it's 2x over 2, so it's just x, right? And we want to find the integral from 0 to 1 of the square root of 1 plus x squared dx. We're like, oh, this looks super innocent. All right, so how are we going to integrate this? 1 plus x squared is what form? Not sine, that's 1 minus x squared. Tangent, right? So we choose x to be tan theta, and dx is going to be secant squared theta, d theta. Once again, changing our limits of integration, 1 equals tangent theta tells us theta is equal to the inverse tangent of 1, which is going to be pi over 4, and 0 is equal to the tangent of theta, tells us that theta is going to equal the inverse tangent of 0, which is 0. So our new integral is the integral from 0 to pi divided by 4 of the square root of 1 plus tangent squared theta times dx, which is secant squared theta d theta. So 1 plus tangent squared is the same as secant squared theta. So then the square root of secant squared theta is just secant. So we have the integral of secant theta times secant squared theta d theta, or if you prefer, secant cubed theta. So what's our strategy for integrating odd powers of secant? So what we're going to do is choose integration by parts. We're going to pick u to be secant theta, and we're going to pick dv to be secant squared theta d theta. So then du is, the derivative of secant is secant theta tangent theta, and the integral of secant squared is tangent theta. So then that gives us the integral from 0 to pi over 4 of secant theta cubed d theta is equal to u times v. So that's going to be secant theta tangent theta, and that's evaluated from 0 to pi over 4, minus the integral from 0 to pi over 4 of v du, which is going to be secant theta v du, and then tangent times tangent is tangent squared theta d theta. So we're looking at this and we're like, I'm not entirely sure that I made a lot of progress. Is this integral really much better than what we started with? Not necessarily, but we can make an observation. What do we know tangent squared is going to be the same as? Well, tangent squared plus 1 was secant squared, so tangent squared theta is going to be secant squared minus 1. So if we put all of that into our integral, we get the integral from 0 to pi over 4 secant cubed theta d theta is equal to, we should evaluate this. So we have the secant of pi over 4 times the tangent of pi over 4 minus the secant of 0 times the tangent of 0, and then minus the integral from 0 to pi over 4 of secant cubed theta minus secant theta d theta. And we got that from just distributing in. So what is the secant of pi over 4? Well, secant is 1 over cosine. And what's the cosine of pi over 4? 1 over the square root of 2, or root 2 over 2. So then if secant's the reciprocal, this is just going to be the square root of 2. And what is the tangent of pi over 4? It's going to be 1 times 1 and tangent of 0 is 0. Secant of 0 is 1. So 1 times 0 is 0, so that part goes away. And let's break this part up into two different integrals. So we have minus the integral from 0 to pi over 4 of secant cubed theta d theta plus the integral, because minus minus makes it plus, the integral from 0 to pi over 4 of secant theta d theta. So now we make the observation that this and this are the same. So I'm going to add that integral to both sides of this equation. So if I add the integral from 0 to pi over 4 of secant cubed theta d theta to both sides, on the left side, I'm now going to have two of them, and on the right side, they're going to cancel out. So I get 2 times the integral from 0 to pi over 4 of secant cubed theta d theta is equal to the square root of 2 plus the integral from 0 to pi over 4 of secant theta d theta. So now, what is the antiderivative of secant theta d theta? So this is the one that I said would be helpful to memorize, because otherwise you have to have that crazy u substitution that is the answer that you won't know unless...
Isn't it secant theta tangent theta?
It's the natural logarithm of secant theta plus tangent theta. So the way we do it the long way, if we don't remember, is you let u equal to secant theta plus tangent theta, then du, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. So then we factor out our secant theta, and that leaves tangent theta plus secant theta d theta. But that is exactly what u is. So we get du is equal to u times secant theta d theta. So then finally, d theta would be equal to du divided by u times secant theta. So we're going to substitute that into our integral, but we need to change our limits of integration again, right? So if theta is 0, u is going to be the secant of 0 plus the tangent of 0. And the secant of 0 is, well, secant is 1 over cosine, and cosine of 0 is 1. So secant of 0 is 1, and tangent of 0 is 0. So we get 1, and pi over 4, we have secant of pi over 4 plus the tangent of pi over 4. So secant of pi over 4 we did earlier is the square root of 2, and the tangent of pi over 4 is 1. So finally, putting all of this into our integral, is equal to the square root of 2 plus our new integral. So when we put in 0, we have 1, and when we put in pi over 4, we got the square root of 2 plus 1, and we have secant theta, and then d theta is du over u secant theta. So the secant thetas reduce out, and we're finally left with just the integral of 1 over u du. So we get 2 times the integral pi over 4 secant cubed theta d theta equals square root of 2 plus, and the antiderivative of 1 over u is the natural logarithm of the absolute value of u, evaluated from 1 to the square root of 2 plus 1. So finally, we plug that in, and we get plus the natural logarithm of the square root of 2 plus 1 minus the natural logarithm of 1. And what's the natural logarithm of 1? 0, right? So we're tempted to say this on the right-hand side is the answer, but it's not quite, because what do we have hanging out over here on the left side? 2. So we have to solve for the integral by dividing everything by 2. So our final answer then is the square root of 2 plus the natural logarithm of the absolute value of the square root of 2 plus 1 over 2. And in truth, you can drop the absolute values because the square root of 2 plus 1 is positive, right? So you don't need it there. And that would be the length of that parabola from 0 to 1. It's the square root of 2 plus the natural logarithm of the square root of 2 plus 1 over 2. So as mentioned, some of these arc length problems look really innocent, and then the integral turns into something very, very ugly. So it's worth noting, you wouldn't have to do that u substitution if you just memorized the formula. You could have just done the antiderivative and plugged in the values instead of working it out, which I would strongly recommend, by the way, because working that integral out by hand every time, while you can do it, it is not worth the time you normally have to do with it. You will save yourself more time by just memorizing that one, because it comes up, oddly enough, more often than you would think. All right. So we want to find the arc length of f of x equals the square root of x on the interval 1, 7. And we want to approximate the integral using Simpsons Rule with n equals 6, and then compare with our calculator's approximation. So we're going to go ahead and set this integral up, and then we'll see what we get. So f prime of x is going to be Well, the square root of x is x to the 1/2, so we get 1/2 times x to the negative 1/2. So that's 1 over 2 square roots of x. So then our integral is going to be the integral from 1 to 7 of the square root of 1 plus 1 over 2 square roots of x squared dx. So we simplify that up a little bit. And 1 over 2 square roots of x is going to be 1 over 4x. So we get 1 plus 1 over 4x dx, which is then the integral from 1 to 7. Getting our common denominator, we would have 4x plus 1 all over 4x. So it turns out that this one, you can force an antiderivative out of this. It does have one. It is even worse than what we just did. That's why we're using Simpsons Rule. With a lot of these types of problems, the antiderivative is either impossible to find or it is an unholy mess. And if you just need to know how long a curve is, a good numerical approximation accurate to 10 decimal places is just as good as having an antiderivative. And it won't take you 10 years, right? So we'll be able to crank this approximation out rather quickly. So this is going to be our f for Simpsons Rule. So for Simpsons Rule, we have f of x is going to equal the square root of 4x plus 1 all over 4x. Our delta x is going to be b minus a over n. So our b is 7, our a is 1, and our n is 6. So that's 6 over 6, which gives us 1. Our x sub I is going to be a plus I times delta x. So that's 1 plus I times 1, so just I plus 1. So setting up our Simpsons rule, if we were to just draw a picture, this one works out super well. So here's 1, 2, 3, 4, 5, 6, and 7. This is x0, x1, x2, x3, x4, x5, and x6, right? And with Simpsons rule, our pattern is going to be 1, 4, 2, 4, 2, 4, 1, right? And out in front of Simpsons rule, what do we always have? Delta x over 3 times, we're going to take these ratios of our function evaluated at the corresponding values, right? So it's going to be f of 1 plus 4 f of 2 plus 2 f of 3 plus 4 f of 4 plus 2 f of 1, I feel like I'm off here. 1, 4, 2, 4, 2, oh, I'm on, plus 4, f of 6, finally plus f of 7, right? And our delta x, as we calculated above, is 1. So we just need to put all of this into our calculator, right? So we grab our calculator. Let's get our f put in. So y equals, and our f is the square root of the fraction. Oh, there it is. 4x plus 1 over 4x. So now we have our 1 over 3 is our delta x over, and then we go alpha trace y1 of 1 plus 4 alpha trace y1 of 2 plus 2 alpha trace y1 of 3 at 39 plus 4 y1 of 4 plus 2 y1 of 5 plus 4 y1 of 6 plus y of 7. Close all our parentheses, and we get the following value for our integral. So the second part says compare this to the value that your calculator approximates. So I've been holding out on you. If we go into alpha window, you'll see choice number 4 there, right? It says fn int. So if we go down to this, you'll notice it puts in a nice little integral symbol and a whole bunch of stuff for you. So it won't do symbolic antiderivatives, but it will let you numerically approximate an integral. So the integral from 1 to 7 of, and then we have to put our function in, so it is the square root of 4x plus 1 over 4x dx. And our calculator approximates it as the following value. So it appears that our approximation is accurate to at least 2 decimal places using just n equals to 6, right? So adding a few more terms to that approximation would give you a few more decimal points of accuracy. So depending on what you needed to approximate that arc length for, 2 inches of accuracy, or 2 decimal points of accuracy may be as much as you need for, if you were manufacturing something, the error tolerance on the machine that's fabricating the part may be bigger than that, so at which point it wouldn't matter, right? So if you're building a disk that has a radius of something like this, but the machine has an error of like plus or minus 0.05, and you're accurate to 2 decimal places, you're going to get something within tolerance anyway, right? Because in the real world, nothing is ever exactly what we say it is, right? There's always manufacturing error, measuring error, a whole bunch of other things. So numerical approximations can be used to help us simplify some of these bits a little bit nicer. All right.